Dear student, myself Dr. Surekha Jaiswal, Head Department of Physics, Moreshwar College, Bhokardan, District, Jalna. Today we will see Bragg's law in course code number 202, paper number 8, Modern and Nuclear Physics. Now today's topic contents are Bragg's law and the Bragg X-ray spectrometer. The wavelength of X-rays is very small. Hence, an ordinary diffraction grating cannot be used to measure it. W.L. Bragg discovered that X-rays can be reflected by the cleavage planes of the crystal. When the rays are incident on their surface near at glancing angle, X-rays that penetrate more deeply into the crystal are reflected from the lower planes are obtained. The intensity of the reflected beam at certain angles will be maximum where the two reflected waves from two different planes have a path difference equal to an integral multiplier of the wavelength of X-rays. Now consider a parallel lattice plane equidistant from one another in a crystal structure separated by distance d as shown in figure. Now suppose a beam of X-ray AB of wavelength lambda. Now as shown in figure, the AB is the X-ray beam of wavelength lambda is incident on the layer of atom in a plane P of each crystal at a glancing angle theta as shown in figure at B, and after reflection goes along B.Sc. See here, this X-ray beam AB is incident at the atom in a plane P of each crystal at a glancing angle theta as shown in figure. Then after reflection it along the ray B.Sc as shown in figure. Now the ray DE, see in figure, the ray DE is incident on plane Q. After reflection goes along EF, see in figure, that goes along EF after reflection. Now reflected rays will be in a phase or antiphase with each other will depend on their path difference, and to find path difference between the two wavefront, draw perpendicular BG and BH. Then the theta be the angle of incident and reflection. Therefore, path difference between the two wavefronts here, that is equal to GE plus the path difference, that is GE plus EH. Now in triangle BGE we get GE equal to BE into sin theta, that G equal to B into sin theta, and G equal to what? B having the, that is value that from this, that is a D, small d, D sin theta. Therefore, and in triangle PEH, EH equal to B sin theta, and therefore EH equal to D sin theta. Now path difference becomes GE plus EH equal to D sin theta plus D sin theta, that is equal to 2D sin theta. If the path difference is an integral multiple of wavelength lambda, constructive interference will take place between the reflected beam and thus the intensity will be maximum. If 2D sin theta equal to n lambda, where n equal to 1, 2, 3 up to order of spectrum, this relation is known as Bragg's law. 2D sin theta equal to n lambda, that is a Bragg's law. For n equal to 1, above equation becomes, here putting the value of n equal to 1, we will get 2D sin theta 1 equal to 1 lambda, that is sin theta 1 equal to lambda upon 2D. Or for n equal to 2, 2D sin theta 2 equal to 2 lambda, and therefore sin theta 2 equal to 2 lambda upon 2D, and from above intensity maxima goes on decreasing as the order of spectrum increases. Now see the Bragg's X-ray spectrometer. Now W.H. Bragg and W.L. Bragg devised a X-ray spectrometer to study X-ray diffraction by crystal. This spectrometer is similar to ordinary fission spectrometer. Here crystal is used as a reflection grating. Now figure shows the Bragg's spectrometer. Now see construction and working. Now it consists of 3 parts such as source of X-ray. See here, that is a source of X-ray, and another part, that is a crystal held on a circular table. See, that is the second part of this X-ray spectrometer, Bragg X-ray spectrometer. That is a here, that is a circular table and a detector or ionization chamber. See here, see in figure, that is a ionization chamber. Now X-ray from the X-ray tube, see in figure, are collimated into narrow beam, see here, by 2 slits S1 and S2. See here that S1 and S2 are the 2 slits having lead plates L1 and L2. From this here the X-ray source, we have get the fine beam of X-ray, and the beam is incident at a glancing angle theta on the face of a crystal. See here, that is the second part, that is a here C is a crystal head on the circular table, and here the beam is incident at a glancing angle theta. Now crystal is mounted on the turntable T. See, that is a turntable T of the spectrometer, which is capable of rotation about a vertical axis passing through its center, and its rotation can be measured from circular scale S. Now most of the incident beam passes straight through the crystal, but some X-rays are scattered by regularly arranged atoms lying in different crystal planes. These scattered rays can be looked upon as having been reflected from crystal plane heavily populated by atoms. The reflected X-ray beam enters an ionization chamber mounted on R, capable of rotation about the same axis as the turntable, and the turntable and arm are so linked together there that taken when turntable rotates through an angle theta, the arm ionization chamber rotates through an angle 2 theta, that is double. So the beam is always reflected to ionization chamber whatever be the angle theta, the ionization chamber current produced by reflected X-ray beam is measured by a sensitive electrometer. See in figure, there is a here that current is measured by that electrometer E. By changing glancing angle theta, ionization current is recorded. If ionization chamber is replaced by photographic plate, the instrument is known as X-ray spectrograph and record the complex X-ray spectrum. A graph is plotted between the ionization current. See here in the graph there is a ionization current in the y-axis plotted and the glancing angle theta here on the x-axis as shown in here. Now peaks A1, A2 and A3 occurred at a glancing angle theta 1, theta 2 and theta 3 respectively, and when n lambda equal to 2d sin theta condition is satisfied. Thank you.